Okay. All right. All right, just
Is that working for you?
yeah. I think that it will be just try to put the streaming here.
Oh, you want to be streaming?
Yeah,
here?
because then I will stream here. I could see here. You know.
Okay. All right.
Make sense?
Yeah.
So important thing. So important thing is that if you can just put your stickers. I know that we are not that much. I will try to record it at times. And something like I'm David, by the way. So just important thing. It's
Okay.
Good.
We're streaming here.
just not put the audio. Just call the audio. Because otherwise, you're going
I'll
to.
cut off an audio on mine.
All right. To see in your programming. The rules that data dictionary. So something that lives in this structure that is data, and you, as a programmer, you're going to tell something that is very fast to compute in, but very good at follow instruction is how you actually calculate data. So you have a function, you say, okay, where I get data, what can I do with this data, and then return the answer. So rules are expressed in code, so that's the classical programming languages, Python, Rust, C++, and then you return the answers from this. So this is something that you're going to learn in these 4 years if you're doing like some kind of STEM degree. Same thing if like you're doing a video game. So you actually say something like, this is an object, this is how the characteristic of the object, what's going to happen when I hit the brick. So if the ball collides with the brick, just remove the brick and then change the velocity of this object. So you are putting the rules into the language, right? And this is something that you're going to learn all this time. So what I want you to think about is we're going to see another way to express, to like give instructions to computers in the sense that we're going to let them figure out the rules. So in the traditional programming, you give rules, you give data, and that gives you the answers, right? And this is going to be the concept that we're going to that people are commonly well versed in working with this. In machine learning, we're going to change this, is that instead of us writing the rules, and we're going to see why it's important that we don't actually make the rules, because we can be really bad at really defining what rules to do. We take data, we take answers, and we put it into this machine learning paradigm, and then we actually let the computer to figure out the rules. So we're going to start with something more concrete. We're going to solve the problem of activity recognition. So the task for you guys to help me out is that we want to develop an algorithm. We want to develop a program that, given sensor from my cell phone, actually tell me if I'm walking, if I'm running, or if I'm biking, or any other activity. So in the traditional sense, what you can gather from your cell phone is the speed. So we can say that if the sensor on the speed is less than 4, you're actually walking. Is that probably everyone probably everyone knows that if your speed is less than 4 kilometers, you're actually walking. So we're putting the rule in the programming language. If the speed is less than 4 and it's bigger, if the speed is less than 4, the status is walking, and else is the status running. So we're putting the rules in the programming language. But this can get So this can be really hard to maintain. What happens when, like, you can say that if the speed is less than 12, then you are biking, and how would you put the characteristics to actually say that you are actually golfing? How do you think that you could put the rules in here? Anyone have any idea of how I could actually put the rules in here if you're golfing?
The phone is on your hand. The phone is on.
Yeah, or whatever. Let's say that you put a sensor, like, I don't know, in the shoes or in the.
It should not consider the first three. It should consider the golfing separately.
But you start to see that it's really difficult to express this kind of things, right?
It's not moving, sway.
It's not moving. Is any other ideas? What would you think that you could give to a computer? To actually like recognize that this is golfing, but it's very different than if you have. Let's say that you only have the speed data of your cell phone. What could you
like some directional sway movement? This is like unique. It's not like this. It's like curve.
Okay. Do you have an idea, right?
I was going to say like the average like speed for each of those activities is going to be very.
Okay, you're putting a lot of statistics to that. Yeah, you could get the statistics and say, okay, maybe this time. But you are doing actually pattern recognition. That's really cool.
The space between both the lines.
Oh, yeah. I mean, if you look like this, bro, yeah. If you do both, you will do something like that, right? But you start to see that this is starting to become really, really difficult, right, to maintain. If you want to do this kind of stuff, you have to imagine that you develop this app, and then in 2 years you have to figure out how to put something else. It's really difficult to like maintain this kind of code, and this is like only 4 lines of code. So in the sense, we're doing what are the rules. So yeah, you start to see what is the distance between the legs, what are the speed, what are the kind of things. Then I gave you the data, so we read the data from the user and we gave the answers. So let's see how we change it. If we actually have the answers, we can actually recollect data from many people in the world, and we can actually ask them, are you running? Are you biking? Are you golfing? And let the machine learning figure out this kind of rules. So what is going to happen? Let's say that this is like the data that you collect from every user that is using your iPhone. And you start to say, okay, if you see this, this is walking. If you see this, this is running. If you see this, this is biking. If you see this, this is golfing. Most of the data that you're going to gather, if it's pixel or speed velocity, can be like it's a binary file at the end. It's just a bunch of zeros and one. And what we're going to do now is that we can actually tell the computer, like, if you start to see these kind of patterns around the data, you can actually learn that maybe if there is 100 here and then 100 in the other side, you can actually say, oh, the guy is walking. If there is like a row of ones, it's running or is biking or golfing or of any kind of stuff. So the way that I want you guys to think about this is that you're going to let the computer figure out this kind of stuff, and in the way that you're going to see is that let the computer figure out the way, even if it's a really bad way, give him a score, and if it's really bad, just try to find a better way to do it. You can we're going to see that we have a framework indeed that if it's something is really wrong, like the score on this kind of talks is really wrong, you can actually tell the computer do a better job. And this is the machine learning paradigm that you let the computer make a guess, you measure your accuracy in this kind of things, and then you optimize your guess, and you finally repeat. So you let the computer figure out like a very stupid way to figure out which is the activity that you're doing. You measure the accuracy, how much is actually good from that, and you optimize the guess, and then you repeat. And this cycle it's just a repeat of all this thing. So when you have these kind of paradigms, you get the label, you get the data, you do the machine learning, you figure out the rules, and when you have the algorithm that it already is very good at figuring out rules, you take the answers from the part and you just take data, and then you get inference. So this is something that when you're training, you're giving answers and data, and this speed up rules. And when you're already just saying, I just want to know what the computer thinks about this, you get data, which takes this machine learning as a model, and then you do the inference. So the model has the rules. Any questions about this? This is something that is really important. So the machine learning paradigm, make a guess, measure, optimize, and repeat. Just rinse and clean. And the other thing is that when you do inference of these kind of things, you just put you just take the answers of the question, and then you just keep the data, and there you're doing inference. So we're going to put this kind of paradigm into solving computer vision challenges. And we're going to use machine learning Tanzania. And that's something that you guys are going to do in the next probably 20 minutes. So I have an image. I want to show that as humans, when we are trying to figure out what an image is, we're going to, our brain is kind of does this kind of process. So anyone wants a guess of what this image is? Okay, but not very specific. Huh?
Is it a person?
Maybe. What made you think of this person?
Could have painting.
Huh? Painting. To the painting. But can you just do the conscious of what actually you're looking in an image when you're doing this kind of stuff? So are there any biology majors around here? No?
What's a neuron?
Guys. So it's important that when as humans, what we understand about the human vision is that our vision actually comes from interaction of the eyes, goes to our T1 of the brain, so our last part of the brain, and then goes to the left and right part, in which the first one can see images like this. So our brain actually have these images like this. And when you travel to the left and the right parts of the brain, you actually are gathering features that are like this. So when the image, think about this image that goes around the brain. When it goes like into the beginning part, it's going to figure out features that come like this. So any idea what this could be? I don't know if the images are not that good. Anything? Yeah. Yeah, you guys figure out at the end. But if I tell you like look at this blurry image, this picture, you figure out that there are legs, there are hands, there is a face on that. So you can actually say, if I have legs, if I have hands, and if I have a face, it's probably a human, right? So something like this is going to happen. We're going to compute and do this kind of algorithm approach to do this kind of stuff. If I have legs, I don't know how to say this, the horse ears, and it's going to the horse. And we're going to tackle this data set. So you're going to see that we're going to have 1,000 images that are like human and horse, and we're going to develop an algorithm that will do this kind of filtering automatically to classify something as human or something is a horse. So our brain, inside of our brain, our brain just does this kind of filtering in the sense that you get this image that is very blurry, and when you process this kind of images, it's going to search for this kind of features. And that kind of features of filtering is something that we want to learn with TensorFlow. So what you actually can gather is that when you have this kind of filters in which you have the image that has these things, you can actually recollect this evidence and say that this is actually a horse. So the question will be, if I have a new image that is not something that I have seen, but if I can say that, oh, this is really slow. If something has legs, if something has hands, and something has a face, I can actually say that this is something that I have never seen. But from the data recollection that I did, if I give this kind of images, it's probably that our model is going to say that this is a human. All right. So, any questions about how the human brain processes this kind of images?
What about the human brain? But in industry, how accurate do you need to be, or how much data is actually necessary? When is the amount that you have enough?
So you're going to see that to generate this kind of filters, so these kind of filters are learned like for at least having this high-level description, like to be able to process an image and then have it filtered that actually see something has legs, something has hands, something has a face. We're talking about architecture that could use 120 filters, right? So the algorithm is going to figure out the best 120 filters to just extract this kind of features. So what kind of images do you need to train 120 filters? Around, something like this to classify. I would say that you need like 200, 300 images or something like that. It's not big data, I know, but at my age, that's something that was really difficult to find. So that's why we need to do synthesized stuff. So we're going to put this to the test. So we're going to make a guess, we're going to measure accuracy, optimize, and then repeat. This is something that we're going to repeat all the time because that's something that they're going to do all the time. So in the terms of computer vision, you randomize initialize filters. So these kind of things, if we have data that's something like that, you're going to start with filters that actually are not going to that can actually just focus on very wrong things like the background and everything. So you start with random filters, apply them to images, and then make a guess which one of these good filters apply to the image that you have. So important thing is that this is not something new. This was something in the 1960s. And if you were like a graduate student in the 60s and 50s, if you gave the exact filter that actually extracts this kind of characteristics of an image, you can get a PhD from Stanford or from Berkeley. So imagine, in the sense that 45 years ago, you get a doctoral degree for just figure out which are the filters that kind of does this. And now we have the capability of just doing this with a computer for free on Google. So this is a field that actually moves extremely fast. Yeah.
I thought we use like machine learning. I thought we use like whole images, and then the machine learning algorithm figures out that this sort of pattern exists among the images.
You are thinking about detection. I'm thinking about classification. So there are two things. There are two problems that we're trying to do. So does anyone have any idea what will be the difference between detection and not you, but what will be the difference between detection and classification? So what would you think? If I'm asking a problem of detection, what I'm actually trying to solve?
What the image is.
Where exactly, right? If I give you an image and I try to detect where is it, right? The other classification will be if I give you an image, you tell me what it is. It doesn't matter if you can find it, if I can tell you something, right? So important here that here we are doing actually it's classification, not detection. So if you're trying to figure out where the image, yeah, you are doing kind of detection. So yeah, so we start with random filters. We start with random filters that apply this to images. Then, I don't know what is slow here. Yeah. Then check how many of your filters. Check how many of your filters are very good to actually match images to labels, and then optimize your guess. Optimize your guess. So use the data that you have seen to say, okay, from all the data that you start, if you start with a random filter, how many good predictions you did in this, and then you optimize, and then repeat. Make a guess, measure, optimize. Make a guess, measure, and optimize. And you're going to see that this is in code. It's actually something like that. So we're going to see how we actually can define filters in TensorFlow, right? So we have this abstraction that is Keras model sequential. So in that sense, you can think of that is define what kind of filters I'm applying to an image. So sequential is something that when you define in Keras that actually have an image and you start to find what are the filters. And the convolution, the max solution, the convolution are just the filters that I was talking about. So you're going to see that convolution 2D stands for two discrete convolution and dwarf. Do you have a marker by any chance? Yeah, can I get off? Yeah. So filters are going to look like this. You have recall that in computer vision, images are just planes of numbers that have red, green, and blue. And with the 2D convolution, what it's going to do is that you're going to find a very small filter like this. So when I was telling you that actually people got their degrees, those degrees, just find out what are the numbers like 1, 2.1, 7.1, 3.1. When applying to this image, like you put this kind of things and then you put it around here, you do a multiplication and everything. If you get very good numbers that can extract, if something is a person of a people, you get actually your doctoral degree. And people start to spend 4 years just finding out which were the good numbers to actually identify cats or dogs. So this is what we refer to a filter. So what the computer is going to do is that it's going to fill this computer with nonsense, with random numbers, and then apply the filters, figure out if it make a good or a bad, or if it made a good guess or a bad guess. If you make a good guess, you're going to fine-tuning these numbers with a method that we're going to see in TensorFlow. If it's not, well, it's not a problem. You just tweak against the numbers to figure out. So in TensorFlow, we have these convolutions. So we start with 16 filters. So we take 16 of these small machines that have a size of 3 by 3. So in the sense that instead of having 2 by 2, here's 3 by 3, something like this. 3, 1, 2, 3, 1, 2, 3. A filter that this marker was more. But yeah, you have like a filter that have yeah 3 and 3, something like this. So this, you apply this kind of filters, right? Then you do a max pooling. So in the sense that it's a way of, if you take an image like this, you want to reduce the size, and when you reduce the size of something, you are forcing the machine learning algorithm to actually figure out which are the important features of the image. And then when you have all the processed all the filters, you can just rejoin all the filters with this dense layer. And with this dense layer, it's a neural network that matches the filters to the level. So you recollect all the information of the filters, you filter them, and then you actually do a prediction if it's a human or it's a horse. We're going to see that. And so this is defining the model. This is defining like what are the filters that I want you to learn. And the second one will be like how you actually fine-tune the model or do a make better guess, is that you find something that is the optimizer. So the optimizer, what it does is that is the way of us telling the machine. The optimizer, what it does is that if the machine did something really good, just keep the numbers that you learned, keep numbers. If it not, just fine-tune again. Wait, something went wrong? Just fine-tune the numbers. And this number, the learning rate, so the learning rate will define a number that is how hard or how soft are you going to tell the machine to change the internal numbers for a good prediction or a bad prediction. So if you have a good prediction, then if the learning rate is low, it's not going to change that much. But if it did a big mistake and the learning rate is high, you're going to see that the filters actually start to change very rapidly. And it's important that you keep on this number like a very low, because you want the model to change small things, not much at a time. So you compile the model, so you have the filters, you have your ways to say that the computer did a good job or a bad job. And yeah, so binary cross entropy. This is something that we tell how we can actually say the model if it did a good job or not. In the sense that binary is that we have a problem that just it's 0 or 1, right? It's human or it's a horse. And what we are going to look is for the metrics for this model is the accuracy, how well it does in those kind of things. And yeah, so all of these things, make a guess, measure accuracy, optimize your guess, are just finding these just 2 lines. And you're going to see that if you decide to go in a career in machine learning, this is probably that you're going to Control-C, Control-V in all of your models. So how actually you give data to the model, so model.feed, the guy who generates the train, and for how many epochs, for how many times you're going to see the whole data, you're going to do it like well. And this is something that you guys are going to do. So if you have, now this is going to be the part that I want you guys to actually go and do something. So please go to this website and tell me that you can open it. So, sorry. Great. So it's Kotlin. Just let me know when everyone has it. Kind of good. Yeah. So, okay. I cannot read. So just raise hands when you guys have the notebooks on your side. I think that's an O, or yeah, I think that's an O, not 0. Or just can you try? I think it's a 0. I was just making sure that you guys were putting me attention. I haven't. Yeah. So you guys should see something that is the demo, right? Something like that. Just let me know when you guys have it. Mhm. So that's the whole reason why I asked the Gmail account. Unfortunately, to actually access this kind of data, you need the Gmail account. I don't know if York use Google Workspace for that. Three.
Is it a 1T?
It's an I think.
No, initially it's 1T, right?
Usually it's a 1, yeah.
Yeah, 1TV, 0, Z, Z, 3, I.
Exactly.
Yeah, it shows not now. Oh, yeah, now it is.
Yeah. Perfect. So yeah. So I'm not. Okay. Perfect. I have.
Kinika.
Huh?
Kinika.
Okay. Perfect. And okay. Perfect. So since we are not that many, I want you guys to follow with me the Colab. You're going to see that actually this is something that you can actually control if you're going to see the repos of machine learning, it's going to be the same thing. And the only thing that we're going to so everyone has it? It's it was an I? Yeah, thank you. All right. Good. All right. You got it? No problem. Probably 1. So. Okay. Are you okay? No worry.
It's on the Google stream. It's on the chat feed.
Yes, go.
Yeah, it's on the chat.
Yeah. All right. So everyone okay with this lookup? Okay. So just before we jump, just I'm going to do a little bit of of an overview of the ecosystem that we're going to work. So what you guys have in front of you is a Colab notebook. The Colab notebook is something that is called RELP. Does anyone want to figure out what are the meaning of RELP? Computer science guys, huh?
It's like representing something.
No? Crash one. Anyone want to guess? I'm going to give you the first. Read.
Repository.
Read. I'm going to say the read. Second one is eval.
Okay.
Print. And look. Okay. So RELP are what you guys are going to find in Colab that is called it's called a RELP. So you're going to find this in many programming languages, and in the sense that a RELP actually it's something that it reads some things, it evaluates some things, it prints some things, and then it loops back the control to something that. So you're going to see this is something that what a Colab looks like. I'm going to do a little bit bigger. I want you to think a little bit more of that, because you're going to, if you decide to go on a career in academics, you're not going to find just Jupyter notebooks. You're going to find something that is called Wolfram Mathematica notebooks, which the license is like $5,000. In the industry, not used too much, but if the astrophysics part, you're going to see that it's quite a lot. So in the read, eval, and print and loop, something that you're going to see in like a language like Clojure or Rust, is that so it reads something, so you can put an expression here in Python, so like purpose string, So it's going to read something, it's going to evaluate whatever it's on the evaluation side, it's going to print the results, and it's going to loop back to give the control to the user. So if it's a terminal, you can call it IPython. If it's on Google, you call it Colab. If it's something else, you call it just Jupyter Notebook. If it's but this idea came from Wolfram Mathematica. Wolfram was one of the guys, astrophysics guy that made a lot of stuff. And this is that it's becoming very very useful in the machine learning side. So I just want you guys to think that this is a computer that actually Google is giving you for free, and you can actually change something like if you go to runtime, you can change the runtime, and you can actually ask for an accelerator like a GPU or a TPU, in the sense that you can actually ask Google to. You're going to see that the algorithms that we work on it's going to take a long time if we don't run it on these accelerators. So you can actually ask for a GPU or a TPU for running your algorithm. So, any questions before we jump into the notebook? Any question about Colab? Yeah.
How did you get dark mode?
Huh?
How did you get dark mode?
Okay. Important stuff, you know. So you play a lot with, that here, then the theme, dark, light, adaptive. I think it's much better if you do lighting like this one, because I cannot see it. Yep. And yeah, the editor, well, I don't know if you guys use Beam. I use Beam, so you move with HJKL, but you can use the default and everything. And something important that I really appreciate a lot is that to show line numbers, because you can actually see where the code fails and everything. All right, so let me just move back to here. So we're going to use Colab, which is a route. So it's something that reads about prints and loop. And we're going to use Tensorflow datasets. So for this workshop, you're not going to. This is not something that you're going to do if you go in the industry or the academia, in the sense that you have like really already clean data to do. So Tensorflow dataset is something that you can actually download datasets and prove your models, but it's in the real life you're never going to get something like a clean data like you get in Tensorflow datasets. So we're going to figure out this kind of things. All right. So if everything goes right. Everything goes right, we're going to start with this. Perfect. So hopefully everyone is looking at the same notebook. Important stuff, if you want to copy, just file and save a copy in your drive, okay? And you can actually have this notebook and you can play with it, you can break it, use your code as your own. You don't have to licensing or everything, because everyone just copy machine learning, okay? So we're going to use a model to recognize feature in an image where the subject can be anywhere in the image. So we're going to classify something, we're not going to detect it. And we're going to do reading a data set that is called Horse of Humans. So the two things that we're going to work today is going to be TensorFlow and TensorFlow datasets. So if you're going to see importance flow as TF, importance flow dataset as TDFDS. For anyone something new, this kind of no, imports and everything, is everyone available with this? Okay, perfect. So the important thing is we're going to start with TensorFlow datasets. So in the workflow of machine learning, the first thing that you want to tackle is gather the data. So how do we actually get the data? You use TensorFlow datasets, and you're going to use the load function. So important things to learn with Colab is that you can actually do something like that. So you bring the imports. You're going to see in the top right corner that is actually allocating the machine. Then it's connected, and it's going to give you the RAM and the disk. So if you guys can actually also ask that the runtime is going to be a GPU, otherwise you're going to spend quite a lot of time here. It's going to annotate, and then you rerun the imports. Perfect.
When would you need a GPU versus a TPU?
So TPU, as I mentioned before starting this, is when you have a lot of data that you want to go through. Like if you have billions of images, TPU become. So its GPUs are like 5 times much speeder than the GPU. So when you see that your algorithm is quite a lot, taking a lot of time to train, you can actually go to a TPU. But in very few cases, I have seen, in very few cases in my experience, I've been in the industry in which we have a lot of data that we need to pass through a TPU. Always GPU. Yeah, because TPUs are expensive. And yeah, sometimes you really don't have that enough data that it really requires to have a TPU. Okay, everyone clear? All right, so an important thing that you can have in TensorFlow datasets and in Colab is something like that. So if you want to know something about the signature of the function, what are the parameters, you can use like, let's say that I don't know what load does. So I can just bring the TFDS load, at the end put a question mark at the end, and at the right is going to show me the documentation for that. So when you don't know something and you want to figure out something, you can just create a new cell, which is a programming cell, then add a question mark to it, and then it will bring out the documentation to that. Very useful tool to do, not only in TensorFlow, you can actually like sort it. You're going to see that it has the signature question key, return a new list, blah, blah, blah. And you can find things. So this. Now, we're going to use TensorFlow dataset load. So this function requires the first argument is going to be the data. So if you want to find which kind of data you can play, so I'm going to show you, sorry. I'm going to show you TFDS TensorFlow datasets. You are going to see that you have a lot of available datasets. So you have from audio, from graph, from images, image classification, object detection, question answering, ranking. So you're going to see whatever I use in this notebook, you can actually use any other image classification and run your algorithms for that data. So in this case, we're going to use horse and human. The thing is that you're going to see that in machine learning, not only you can actually do this kind of things in which you have the data on the label. Sometimes you want to do machine learning, something that is not on label. But for this Colab, we're going to use that is a supervised training. So we have the data and the labels with info. So in that sense that we also want to have the info piece up. So we evaluate dataset and info. So we, on top of this kind of thing, in the dataset dictionary, is going to be a dictionary where we're going to find the data, and the info, we're going to have the information of the data. So if you run it, it will take a while to download the images and the size. Yeah, so you're going to see the dataset horses or humans dataset is downloaded and prepared to this kind of thing. If you print the info object, everything went well? Perfect. You're going to get the information of the dataset, which is the name, which is the version, what kind of description is the dataset, where it comes from. Important thing, what are the features? So if you can see here, the dictionary that we gather here, this object, dataset dictionary, has two things, images, and the images have in this shape, 300, 303. So anyone wants to explain me what could it mean that the images are 300, 300 by 3? What are the description of these images? I think
it might be 3 dimensions.
Nope. What could it be if I have the images are 300, 303?
It's like rows and columns.
So we have three, yeah, which in one you find the channel color, so these are the 3 of them. And the size, the height, and the width of the image is 300 by 300 pixels.
I think I'm not wrong.
Ah?
I think I'm not wrong. By assuming it's like a 3D matrix.
It's a 3D matrix, but it's a 2D image, right? Because you can actually have like images that have that, right? But and the labels, so if you can see the shape, it's an empty thing. So that means that it's a scalar, right? If it's a scalar, something that it's an integer, you can see the type here, it's an integer, and it only have 2 classes. So it's only 0 or 1. The total number of examples is 1,283, and the split of the data set is that in test we have 256 images. Thank you. And 2,000 images. So you have the information. So now we're going to explore the data. TensorFlow dataset comes with this amazing tool that is called as data frame. and receive as argument the dataset that you want to say. So since this is a dictionary, we're going to see that this is, you take type dataset dictionary, to become a date. You can actually see which are the keys. Dataset keys. You have test and train. So when you pass the data set, here I'm shuffling, just assume that this is something that is shuffling and taking 4 data, and you get, which is the images. So you have, I have here human, horse, and horse. So if by looking at this data set, do we have, are we having the clear idea of what we actually want the algorithm to learn? Is everyone clear on that, in that sense? What are exactly what the tasks that we're looking for? You have a question?
I have a question.
Yeah.
What if my images are grayscale?
Huh?
What if I have images that is filled in the grayscale?
If you work grayscale, you won't have the 3.5. Just will be like something here. So you only have one of this. And if it's grayscale, you assume that each pixel that you have here is between 0 and 255, or like 0 and 1, and it represents how black or how white the image is.
So I will do 301?
Yeah, exactly. So 300, just
Yeah.
one pixel.
Thanks.
Perfect. So yeah, so what we actually want to learn is to develop this algorithm that even this image actually goes human, even this image actually goes horses. And if you see something this here, human and horses, right? If you copy exactly the same code that we have on the slide, so we define filters, we define what kind of the size of filters, these activations and everything. This is something that is outside of the scope, but this is something that you want to do to learn which are the good filters. So you evaluate them all. If you want to know how many numbers are we learning, like how many of these numbers the model is actually fine-tuning. So we have 40,165,409 and 409 numbers, in that sense that we are going to let the machine learn is which are the best 4,165,469 469 numbers, which are the best for gathering these kind of results. This is actually a huge number, and you're going to see why it's important and what's going to happen. And then we copy like the code that allows you to define how good or how bad the model is, which is the way to actually learn this better representation and what kind of metrics are you going to find. So before we send this model to train, I want you guys to see something here. If we take one of the images of the data set, if it goes right. So the shape of the images is 300 and 303. The max number that you have is 255 in that images. So in the sense that if you take a look at all the numbers that we have here, the maximum number is 255, and the minimum number is actually 8. So the question that I want you guys to think about, is that really important that the numbers go from 8 to 255? Is that really important to the characteristic of the images? Why?
Because if it's going, then we're talking about the restraints or restrictions between the patterns that we can find.
But so it might be another decision, but if I can rescale it to 0 and 1,
Makes it faster or easier to deal with the data. If it's like under restraints.
So it's always a good idea that the data that you present on a neural network actually goes from 0 to 1, right? You're going to see that you're going to do this kind of rescaling stuff right here. That you want your minimum to be 0 and the maximum will be the 255. This reason of 255, you're going to see if you're interested, is because our images actually are type unsigned integer 8. In the sense that I have 8 bytes, I have only 8 bytes to save the pixels. So this can be 0, let's say that all of them are ones. So the biggest number that I can represent is actually 256. And if all were zeros, all will be zeros. So what I can do is actually just rescale these kind of things to just move between 0 and 1. It will be much better to algorithm to do. So to do the data processing, you just need to, we're going to do this kind of rescale. We're going to do this kind of rescale in which we take the data sets, we define a sequential thing. So what can I want to do to the images? Rescaling between divided by 255. So the 255 becomes 1, and the 0 divided by 255 is 0. And yeah, so the map is a function that for each element of the data set, what I want to do is just take the image, take the label, and then just rescale it under the label. And then if I want to shuffle the data set, because it will be important that you present the data to the algorithm in a shuffle way, and then batch it by examples of 32 images at the same time. So if we define these kind of things, now we're going to do the train. So if you take a look, the model.fit just receive obligatory the signature is going to be X and Y. So here, we're going to take the train from the dataset dictionary. We're going to shuffle and we're going to repeat it infinitely. And the validation dataset is going to be just for the test one. So what we want to do is actually, we save a little bit of the data that we have just to figure out how good or bad the model goes. And we let it train. And you're going to see that if you try to do this without GPU, it's going to take at least 1 hour to go to the whole dataset. But if we do it with the GPU, we reduce the time to over, if it goes right. Yeah, so whole epochs. If you want, just try to change the runtime, but you're going to see that this is going to be extremely slow in a computer. So the important here is the loss. So the loss will indicate how bad the model is doing on the dataset. The accuracy is going to figure out how many of the good labels we actually run. The validation loss, how bad the model does in validation, and the validation accuracy here. If we finish here, we are going to see 2 epochs of 15. Let us wait, 14 and 15. So if you evaluate this, you're probably going to end up with a very low loss. The accuracy on the data set is like 90%, 0.94. But take a look at the validation on the accuracy side. On the accuracy and the validation is 0.7. So when we show the model data from the trained data set, it's actually 94% accurate. But when we show images of images that are not in the trained data set, it's going to get like only 70% of that.
So what's the difference? Like, this is an over accuracy.
That's something that I want to discuss. Does anyone have any idea why this behavior? What will happen that when you train something in the trained data set, you're very good, but then you move? Just any ideas? What could be wrong? Yes.
Maybe you're training one kind of data and you're testing it on some different kinds of data.
So that's object. That's really good. You actually people were doing this in the 2000s, forgetting the thing that you actually mentioned. It's called the data drift problem. These markers, not good. The data drift problem. It took 4 or 5 years of research, people. So really cool that you got it. So yeah, it could happen to the validation. So I want you guys to investigate if the validation images are really that different from the trained data set. That's task number 1. What other things could happen here? Any other ideas?
It's like a skew or a bias.
It can be a skew to bias, but why in training and not in the validation? So it will be important. The task that I want you guys to have with this notebook is try to see how you can actually manage to print one of the images of the validation, and you tell me if actually something that you can see in the trained data set or not, right? The other thing that you guys know is that, does someone know, anyone here about Occam razor? Occam razor. The principle of Occam razor. Google it. I will ask in 2 minutes. And when you get the Google and the information about Occam razor, I want you guys to tell me something. How can relate the principle of Occam razor to things in machine learning? So, what is the principle? Sorry, I want to see your name right. Sorry. What is the principle of Occam razor?
It says that it's a model that states that it's able to do more with what can be done with fewer. So you're basically taking less to make same number of assumptions, and, like taking more instead.
All right. So, what it means in the long term is that I have two competing hypotheses or two models that actually do the same thing, that is really good on training validation. The one is a philosophical statement that the one that we're going to choose, the one that has less parameters because it's less complicated. So this is the principle in science that we are going to also use in data science. When you have two things that explain learning how to predict a human or a horse, like some kind of thing, you try to always take the Occam razor into account, that you want to have a model that doesn't put a lot of parameters. So that's why it was really important that I want you guys to see this kind of number, that 40 million of parameters, 40 million of numbers, you need that you can put them there. So you're actually, take into account the magnitude of this number of numbers is actually encoding very, very, very complex rules. The second task for you guys will be, can you try to reduce the kind of numbers and figure out if reducing these kind of parameters actually reduce the number of the skew between validation and training. So first task is try to plot images of the validation dataset and figure out if it's a repetitive problem, as you mentioned. Second one is try to figure out how we can reduce the number of parameters. So just a hint, try to play with the numbers, how many filters you can put here, what happens if you delete one of the max pooling of filters, and then retrain the model, right? And play with that. So that's notebooks is for you. And this is something that we're going to do for the 15 minutes. The other thing, the other that we're going to have here is in this part of the code, you can actually upload images from your computer. So if you evaluate this kind of notebook, you can choose files. I'm going to choose like this image that is a horse. I can select it. And the image that I trained, the model that I trained, and I gave you a horse image, is telling me that it's a human. So try to play to see if you can actually gather a model that when it presents a horse, it actually represents. And just to, like, the cherry on top is to figure out the relations of how the filters look like. So I'm going to take a very, very image from the trained data set. And for each of these filters that we have here we have three filters. The filters look like this. Maybe you can see it. The filters look like this. So much brighter, which means that the model is actually putting attention to that. So take a look. This is actually a human, or I think so. It's a human. Hopefully, we are going to see that the model is actually putting a lot of emphasis into like things like head. At the end, when the images are too small, it's actually like look at the non-activated part, like the very dark ones, which are almost zero, are like backgrounds. So it's not put into that. So the model is learning these concepts of what are actually a human and what is actually background. And this is this is one of the computer hypotheses of how we do computer vision in the human brain. All right. So, tell me.
Isn't this basically a test of whether is there a human or is there not a human? So like nothing into horses. Just like, you know.
But actually, I can say, yeah. So if you show something that is clearly not a human, it will say that it's trying to say a horse. So, yeah, you're good on the spot. I'm really happy that you're gathering this kind of insights. But yeah, you can actually have like a train category that says not human or not. But yeah, the model will be as good as the data it has. So if you just show humans and horses and you pass an image of a cat, don't expect the model to learn that out of the blue. All right. So we ended up the what? It's 17:28, so it's 5:28. I'm going to give 50 minutes so you guys learn the notebook and something. So 2 tasks that I want you guys to see is that you show me a different model with a less number of parameters, right? The task, and to evaluate one of the images that you can find on the internet with your model. So are those 2 things clear? Gather a model with less parameters and evaluate the model with a new image that you find on the internet. So you have all the coding there, and I'm here to answer questions. Is that clear? Make sense? Perfect. All right, so 50 minutes, and that's it. I will leave you free on the Friday. Is that everything okay? You got it?
Yeah.
Yes. No problem. Okay. So, anything that you want to ask?
I was expecting a beginner session.
Oh, so in which part do you think that you might not understand?
Yeah, most of it.
Let's go to the code.
I don't know what these things are. I haven't seen it before.
Okay, perfect. So do you understand, do you recall what is a rel? So read, evaluate, and print. So whatever you put here, the computer is going to read and evaluate this kind of things.
So these are the parameters.
Okay. These are like the libraries that we're going to use, right?
Yeah, you import the Tensorflow.
So just imagine here that has Tensorflow data. That's good, right? So we evaluate this, we bring these tools into a computer.
And I just took a guess.
Right? So TFDS, this function, where does it come from? Where is TFDS? You can see it in the upper part of the code.
Right.
Exactly. So the TFDS comes from the TensorFlow Datasets library. All right?
Yeah.
So the TensorFlow Datasets library is doing the function load.
When it loads,
Hmm?
it executes.
So the loads, so recall, so open, can I click?
Yeah, brings it down to the
So,
keyboard.
yeah, so let us put something, I can release, here's something
I
like
mean,
that.
if we like undo, we just
Put something like that. Oh. So I want you to write in here, TFDS, like, another dot, load. And then the question mark. No, no stress about it. Yeah. I think it's, yes, click up because we haven't run the imports, so we might need to first bring the. What? What did you do in our computer? All right. So, these things install the libraries on computer, right? Right. So evaluate it. So you can actually go clicking here or shift enter in here.
Right here.
No problem. This only brings the libraries into the computer, right?
Yeah.
So evaluate it.
You
Because
could just show me click it.
yeah, you can click on the play or just
the
shift
play
enter.
button.
Yeah. So in that sense, when you evaluate it, it's going to bring these things into the computer from the cloud.
From the server.
Right?
Yeah. Okay.
Now open a new code cell. So you can see that here's the code, right?
Oh, sorry.
No problem.
Yeah.
Right? I'm going to do things. It's just my computer is a little bit weird.
Yeah.
Now try to take from. We're going to move it around here. Just that evaluates after this.
Yeah.
So I want you to investigate how the tfds.load function works. So you
Yeah.
can do it by this. So copy the tfds.
Let me decipher. TFDS.
So that is telling you the computer, okay, I want to use this library.
Yeah.
So with point, you access the multiple functions that are in this library. So do point, and you're going to see that there's going to be a lot of functions on there. So do a point on that.
Load, right?
And you see, no, just before the load, you can see that there is a lot of functions there. So this
Yeah.
is code that someone else wrote for you to make your life easier.
Okay.
All right, so we're going to find
Seems like a recommendation.
exactly. So just go for the load like that, and then end with a question mark. So this allows you that when you're working in Colab, if I want to know what the hell is TFDS load doing, you can evaluate it by that. So just evaluate it, shift enter.
Shift enter.
You're going to see
Oh.
the documentation of this kind of things.
So we're just like pulling data for the data.
Exactly. So the TFDS says loads name into a TF dataset, whatever the hell that is. All right.
Yeah.
So if you see the number, the name, we're going to make just a copy, just to not say copyright.
Did you pre-made data from Tensorflow or did you make it yourself?
I didn't do it. It was a colleague from Google that made it. Yeah, it's something that we use for workshops. So just at some point when we're doing like the analysis and this kind of new data, you get sued because apparently data has ownership now.
Oh.
Okay. So you read, you evaluate. Okay. I'm going to change this session. I'm going to use this one. A moment ago. Sorry. Sure.
So the code is Python, right?
Yeah, the code is Python. Just hold on. Save. It changed. So the important that I want you to do you have a copy of the Colab in your iPad, right?
Yeah.
So try to put the two code cells in here, and I will put questions about that in my computer. Okay? You need to evaluate those kind of notebooks that you have here. Try to copy in here, and I will have questions about that. The three of them when you have the images up to here. Okay? So copy that, and I will have questions about it. Right?
Copy the image.
Copy the commands. Okay. So this is a command. This is a command. Yeah. This is a command, and this is a command. So my objective for you is that you actually gather be at this point. Okay. And I can see because I'm sharing the screen. Perfect. Does it make sense?
Yeah, so I just copy the whole
In my computer.
Yeah, I think I can run this.
Yeah. So go for it.
So copy the whole.
Was it good? So,
Here's the difference between the activation functions and the like ignore an idea.
yeah. So, you guys do math and physics, right? Well,
I did computer science.
okay. So, the problem is technically one thing that what I didn't write is I omitted. When you apply, just multiply it. When you like 1, 2, 3, 4, 4, like 1 times 4, 2 times 4. This thing is linear, right? So if I have a function fx equal ax plus b, I have a function dx, w x. What happens when I do f of g? Are you sure? So for me, f for this, f of b is f. Yeah. So f. So you are going to see that f equivalent to w x plus b. F equivalent to w x is going to be a w x plus b plus b. So if my math doesn't fail, AWS, CAD, I can represent this by D, and I can represent this by C, right? So, composition of linear functions is linear function, right? So,
That was a multiplication, that's why I said it's important.
so in a high level of things, you are learning from, like there is a framework you can actually learn that all the things that we did, you are learning functions. So if you're there are very small things that you can actually model with linear functions. So if you want to learn the more complex functions, what would you think that we will need to change in here to make this not linear? What do you think? Any guess?
We pick parameters in such a way that it is not linear.
I will just create a function that is like this. I want you guys to X, which is? We're going to find a function value of X, something like this. X if X is bigger than 0, and 0 if X is less than 0. So, what do you think this function looks like?
No, just just straight line, 1, 2, 3.
So, X is if it's X
Greater than 0.
zero.
Yeah, so for 1 it would be 1, for 2 it would be 2. Yeah, so sorry,
Right.
yeah, that.
And it's 0. Right? This is more the simple non-function, right? Non-linear function. It's like function linear here. This is right. So you are adding a non-linear function to be able to learn non-linear functions. That's
People prefer value over sigmoid in machine learning.
that depends. So sigmoid, you see it's a linear.
Yeah.
So sigmoid is actually this actually is to learn non-linear functions.
Yeah.
Sigmoid allows to learn distributions. So distribution is if I have a vector and I want to transform it into a probability distribution, I turn it to sigmoid. So at the end, models are learning probability distribution in the sense that you're learning, given an image, what is the probability of this to be a human or a horse. So when you want to control, so this thing is to learn nonlinear functions, but when you want to learn a distribution,
Yeah.
you want to learn a distribution.
Oh, so if you comment the line 10, like that equation value part, this one, it gives us a better output than before. That is because it is not linear. Like it's not a distribution, sorry. That's why it is giving a better output.
Yeah, and this will not work because you have a plot. Oh, you have a plot, so you have a huge vector. But at the end, the distribution is how many plots? We only have 2 plots.
Yeah.
So we actually need to have this kind of dense connection.
Oh.
So just
So we need to remove that.
you need to remove filters. So the whole idea was just to remove filters. Just remove like filters or reduce the number of filters that you have.
Okay.
Or you can just reduce these are the numbers of filters. So maybe it's 16, you can, or maybe 32, so just 16 here.
Okay.
That's the, just working with data, it's not parameters at all, but data you can. Well, it depends on what you want to do, but,
So the first orders are going to happen the same thing that happened in the heads. The first orders are going to learn like very circles and lines. Second ones are going to get that information, yeah, like if it's shoes or like so it's always good to just reduce the number of filters.
Oh, so instead of 64, we can do 16, and instead of 32, also we can do 16.
And figure out the number of error, train the model, and see if actually we can reduce the parameters. All right? Make sense?
Yeah.
Perfect. All right. Good?
So I'm thinking of 2 things. It's overthinking.
Okay.
So there's even 2 possibilities. We can either get more data, which is not our case, or we try to use existing techniques like dropout or regularization. We're not trying to figure out how to actually apply it in the analysis.
Okay. When you try to do this kind of thing, dropout and regularization, it's in the sense that
Okay, so it basically adds.
so we're going to start with dropout. So a dropout is actually when you have filters, you see the number of filters. You say like you know what? I'm going to tell the model that I'm going to drop four random filters. Okay. So you are forcing the model just not to depend on the other filters. Right? But this is like a more advanced stuff when you already know that if you reduce the number of filters, then you import the model. So the first thing you always try to do is to reduce the number of parameters. The reason is, can you be more specific when you say it's simple? You use
less parameters to conclude like it's either a man or a horse.
But the principle that I want you guys to hear is that I want you guys to see if we apply open ratio. Right? We have a model that has less parameters. Exactly. So you put philosophy into this thing that you need to have a model that has less number of parameters, right? Because when things are simple, if you have two complicated hypotheses of something, you should always choose the less complicated. So
the output is way too complicated. The output is way too complicated.
No, because you're taking the model and you say, I'm going to drop one of the filters. So actually, you're reducing the model.
Don't care what color.
Yeah, you can just, yes. What happened if, if I drop the blue channel of the image, I will still have a human, right? But if you have like, yeah, exactly. So, dropout, it's not that you actually, dropout is that you force when you are training, that you actually allow us to choose R, T, or B, just drop the channel, right? So this kind of stuff is already when you have the number of, like the correct number of parameters. So when you drop one filter, it just hurts the numbers. So the first thing that I want you guys to take a look at is to reduce. Yeah. I want you guys to give me like a model that has more validation with a number. You can use robots. So let's see how it goes. I'm pretty sure that you can work. This is black magic, so
Yes,
I cannot.
You don't know until you apply it.
You don't know until you apply. Good. Good. Are you okay?
Good, but it takes a long time.
Recall that you need to ask the DPA. Oh no, it's yeah. It's just security. So you got it?
No, I'm not really sure which
Don't
code to
worry.
copy.
So the first thing that I need, bring the libraries. How do I bring the libraries?
The
Imports. So
TFDs.
I will start with copy the imports, right?
Yeah, TFD, Colab.
Copy and paste. You got finished?
No. By increasing the filters, the parameters are increased. Yeah.
You reduce the number of filters. Can I take it?
Yeah. Now we change the
Alright.
parameters.
You change the runtime to CPUs?
Yeah.
Questions? The most, the number of problems. Okay. So the important thing is that you can actually change this. You can actually copy it, store it, but what is the number of parameters?
2, 4,
If you reduce it, so maybe something in the middle. Make sense?
Oh, it's very
Yeah.
fast.
Yeah.
Okay, but I can have
Clear?
Oh, yeah, because it was already done.
But
Oh, yeah, the side.
yeah,
Sorry.
no problem. You have to do the same things earlier.
no, all of them is 16.
So when you have something like that, you don't call the function just like this.
Oh,
All right?
okay. Yeah, yeah.
Perfect. So the important thing that I would love you is you can take a look at the Python. Like I'm going to recommend you that you start with Python real
But then it was not,
core.
can you repeat the activation?
It's a very short course, real world Python. Should be free.
Yeah, I have actually this book.
Yeah. So just add that. It will make it will.
Yeah,
Then after
actually-
that, it will make these things all
Yeah,
kind of sense.
like I'm in my first semester,
Mhm.
so yeah, we're doing JavaScript now. But I know, like, I have a previous experience with Python.
The thing is that as soon as you get your first language, you're going to see that you can interpolate. So
Yeah,
you can learn one language, and you can actually move to different language.
yeah, it's pretty much not difficult to understand the others. Yeah, so once the data is pulled, so what am I?
First, you bring the libraries. So in this thing, you bring the libraries,
Yeah,
and with this tool, dataset.info load, you bring the dataset, the data down here. Okay. Right. So just a note on here. So yeah, at the beginning is put an effort into learn Python. It will pay off in the future. Just trust it.
okay,
All right.
yeah.
All right. I will have like only 5 minutes. I have to go.
Reduce the number of layers, but then the number of parameters doubles.
Which one? Show me.
I'm not 100% sure.
Yeah.
I don't know how to
No, that
tell
would
it
be
to
more
take
than
only
1.
like 2 channels instead of 3.
In which one? Tell me which.
This one. I reduced the number of channels.
Yeah, but
Are you a
the
first
thing
time
is, you
coder?
cannot change
Are
the
you first
data.
year?
Because you
So
can
it's gonna be a
So
little
how
different,
did
right?
Yeah,
The number of
I haven't
filters
seen
defined
such concept before.
16
Yeah.
filters.
So me neither. I'm actually in math, not CS. I'm not really
You don't change the data.
Yeah.
That would be
You like
that's
I'm
that's
in my third year. Yeah.
if data science from our religion,
But don't worry.
Yeah,
you're
I
committing
want.
the biggest sin that you cannot.
Yeah, but it's
you
kind
cannot-
of thing for you to.
Yeah, it's enjoyable.
Okay, questions, doubts, you can add me on LinkedIn, my email, you have my email, right?
Yeah, I'll post his LinkedIn in the
Yeah.
on Discord and on the chat, so you guys can add him on the LinkedIn.
Yeah.
Ask him any questions you guys have.
Yeah, I'm very open, if you guys are interested in positions in machine learning, and Quebec, really nice part of the country. Yeah, just feel free to ask me whatever you need. I'm here to help. Okay.
Perfect.
Clear for everyone. Hope to everyone to see you in my LinkedIn or just write me an email at the end. Open to questions and doubts. Okay.
Yeah. So thank you everyone for coming in. I hope this is the first of many in-person workshops where we, invite someone who's get really hands-on with anything. But yeah, thank you very much for coming to our first in-person workshop, and we hope to see you again soon. And thank you to everyone who was online. I don't think anyone's there right now, but thank you to all the people who were here online before we started really getting into hands-on stuff. But yeah, I hope we see you guys again soon. Thank you very much.
No problem. Okay.
Yeah.
Okay. I will copy you.